name is Yun Guan, a professor in the Department of Electrical and Computer Engineering at Iowa State University. And EviHunter is a project collaborated with the NIST Computer Forensics Group, Barbara Goodman, Rick Ayers, and Jim Lau. And we target on analyzing Android apps and with the purpose of discovering, identifying digital forensic artifacts. So nowadays, virtually everyone has a phone, maybe more than one phone, mobile devices. And we see a kind of quickly, rapidly evolving technologies from hardware to software to business applications. And accordingly, we're seeing a lot of kind of increasing use of mobile evidence in cases, in both physical and cybercrime cases in US and globally. And the FBI, the former FBI director, Jim Coney, and he said, so in most investigations nowadays, the single most important piece of evidence is mobile phone. And let's start from a few statistics about mobile app markets. And in 2021, and Google Play has 3.14 million Android apps. Apple App Store has 2 million apps. And a few other app stores like listed on the slides. We have Amazon App Store, Tencent App Store. And actually through our study, we found over 60 other third-party app stores. And so the figure shown here is the number, you can see the number of apps increasing monotonically to a point that's around December 2017 and 2018, and go down a little bit. The reason for that is because Google Play, the Google App Store, has done a cleaning up work at the time and tried to remove those outdated apps and also to remove those some malware apps they detected. And we're seeing that in the last couple of years, we're seeing the most downloaded Android apps, including Zoom and a few others, mainly because of COVID-19 and most people work from home and remotely, and they use those conferencing apps and to have meetings and to work with colleagues and so on and so forth. And this associated the top Android app category in 2021. And you might think so Google Play and Apple App Store are the major ones, but actually starting from 2 years ago, this is not true anymore. We're seeing so that Google App Store and Apple App Store are only the number 4, number 5 app store. That means that other app stores become more popular and they're hosting more new apps and so on. So in 2020, there was a survey data shows about, right now we have over 8.9 million mobile apps. But neither Google Play and App Store have the most new apps. And also another data shows in 2020 and 2021, averagely, so each phone has about 40 apps, but there's another data shows about 80 plus apps on the phone devices. And from there, traditionally, crime investigation focusing on financial frauds, human trafficking, drug trafficking, and theft and child porn cases and so on. But it's very unusual to see some cases in the past that are relevant to mobile evidence. For example, the illegal animal poaching that happened in 2017. It was one of the biggest animal poaching at the time. So this is a group of hunters, illegal animal hunters, and they have almost 20 some number of trips to the southwest of Washington, and they kill animals. And they're not trying to kill the animal for meat, for the hide and others. They just kill the animals and shoot about. They left the body in the kill site. So there was an investigation that's kind of interesting. So this group of 8 hunters, and they actually use the mobile apps, the social media apps to share videos and images. And so many of the images and videos, they have the geotagging information. So the case starting from the surveillance camera to capture a few of this hunter in the group, and actually use the GPS location to find all those kill sites. And then so the text messages and social media information exchanged on Facebook and others. And so and also plus the shotgun slug and others. So they used to solve the cases. In this particular case, so the mobile evidence plays a very key role to solve this case and identify those hunters in the group. There was a kidnapping case in 2017, and this girl's name is Ying Zhang, and she was a visiting scholar at UIUC on Urbana-Champaign campus, and she was reported missing in June 2017. And so since reported, and local law enforcement, the UIUC police departments, and also FBI was involved in searching and trying to find where this girl was at the time. And so in 2019, almost 2 years later, the cases was solved. And so one of the PhD student, because one of the PhD student, Brandon Christensen, was the one that linked to this girl and actually raped, he admitted a rape and killed this girl in his apartment. So now the question becomes, so immediately after this this case happened, and when I taught the class, my computer CPR 566 computer forensics class at Iowa State University, I mentioned this case to my students. And so it was an interesting issue that happened because it took almost weeks and even months to find where this girl was. And so eventually find the blood and other evidence from the apartment, the bus stop in the apartment of this Christensen. And so the question becomes, so why it took so long to find the linkage between the two persons and the lady and then this criminal. And so, at least so when the girl was stepped into the car, the small black car, Christensen was driving, and they should be together. And so maybe there's interesting evidence available. For example, the two cell phones may be connecting to the sequence of cell towers. And by using that sequence of cell towers, we probably can find the relationship between the two persons. And so, but it was, until now, when I searched for news, and we couldn't find any news that cover this type of information being used. If we are able to use this information, we probably can find this girl quicker, earlier, and maybe there's a hope to save the girl's life. And then, so since then, so the body of the girl was still missing, and we cannot find her. Interestingly, so 1 year later, in 2018, November 2018, Thanksgiving week, there was another case in Colorado Springs, and this related to Kelsey, Berreth, and Patrick Frazee. And so the girl is the mother of the 2-year-old girl, and so the Patrick Frazee is the boyfriend, and Kelsey was the fiance, one-time fiance for the man. And so the girl was reported missing, and so Patrick Frazee said they were not together, but actually they look at the phone records, the call records, and also the text message. They find this is not true, and they prove that so Frazee actually lied about the fact that they were together during that time period when the girl was missing. And then so this, in this particular case, there wasn't that much about physical evidence, and so the mobile evidence, the digital evidence become the very critical information to be used to solve this case. And then they got a search warrant and obtained the phone call records from a cell service provider like Verizon, and they put the relationship and also prove the fact that so the girl was killed by the man. And so there was another lady, Crystal Lee, is actually a person who was hired by Patrick Frazee to clean the bathroom. There was a blood and other evidence available there. And so Crystal was sentenced for 3 years. And so the Patrick Frazee was sentenced for the whole life in prison. So from there, so let's review the current practice in terms of the mobile device forensics. Years of the investigators, the practitioners in the crime lab, and we starting from the physical acquisition means we seize the phone devices, we search for the crime scene and seize the phone devices, and try to figure out a way to image the evidence from those devices and then bring back to the lab and for further analysis. And years of investigators use the licensed toolkits like Celebrite and EnCase, and they usually use a keyword searching to find, for example, location, phone call records, doc messages, saved contacts, and calendar entries, and so on. So the whole process mainly is a manual process. And so this associates the frequently used forensic artifacts, and including the browsing history, as we mentioned in the UIUC, in John's case, they use the browsing history to find. So the Christensen actually used the phone devices search online and learn how to kidnap, how to kill a person, and so on. And also Wi-Fi connections and user accounts and geotag information available, and also pictures and videos and audios. They're all frequently used forensic artifacts. And then so the final stage of the investigation process ends as evidence discovery and reporting. And so some kind of screenshot that help to answer some of the forensic questions, investigative questions, and so on. So there certainly are challenges from the current practice. So the first thing is the whole investigation process is time consuming. And remember, so we have almost over 8.9 million apps for the whole world. And also averagely, so each phone device has about 40 or even more number of apps on the device. And the whole thing takes a very long time to process this. And so when we visited Houston Forensics Center, the mobile device investigators told us, so they are spending almost 1 to 2 days for one single device. And so in this case, that's kind of one of the main reasons that result in the large backlogs in crime labs. This is a common issue for most crime labs, from the federal level to state level to city level labs, and so on. And the other things is error prone. This kind of process is completely based on the manual work. And so it highly depends on the investigators' expertise, experience, and so on. And so this often has a problem, like completeness problems and accuracy problems. And so because of the lack of expert knowledge about this number of apps, so the manual process means the investigator has to look into every single app, their folders and SQLite database, and find the relevant evidence like locations and time and other information there. So this lack of expert knowledge often led to inability of identifying, discovering evidence, or maybe sometimes misunderstanding about the meaning of the evidence collected from the phone devices, and so on. This leads to error-prone investigations. So subsequently, it may another contributing factor for the large backlogs, because the investigator has to pay extra attention and extra work into to guarantee the foreign artifact discovered actually meaningful and relevant. And the other thing also lead to issues like consistency issues, and it may be related to quality assurance, because investigators use their own with a different level of expertise and experience and working in the different labs. Sometimes they are repeating the same casework, and sometimes they can come up with kind of inconsistent in their findings and conclusions. So this all kind of challenges are very difficult to solve because of the issues involved in this evidence analysis. So let's review, let's discuss a few interesting examples. And as we mentioned earlier, like the animal poaching cases, and also the Kelsey Berreth case, the Patrick Frazee cases. And geolocation information is very frequently used evidence type and being used. And so people think this is very trivial, right? We just search for the phone devices, and in the app log file, or maybe the SQLite database table, you may find the geolocation information like latitude and longitude values. Maybe it's so trivial, it's not a problem at all. But in reality, this is not true. And so sometimes we're seeing in the app logs and also in the SQLite database, we may now have the information, for example, what the number means. Does it mean latitude or longitude or something else? So if you look at the number, like just like a string, a string of numbers, the two examples I showed here. So how do you know this is GPS location or it's not something else? If it is a GPS location, which one is the latitude value, which one is the longitude value? And so through our study, we find there are some apps developed in Taiwan, in the Asian part of the Taiwan, and they actually reverse the order. So that means if you're looking at this number, that means a different location, not the location we usually consider as a true, like as a fact, like latitude first and longitude the second, but usually the other means a different location for the same information there. We also see some similar problems about time format. And so in US, we use the like month and day and year in that order, and also time zone information there. But what about if you look at the app logs and also cache space in the memory or the phone device and the SQLite database, you find a sequence of numbers like a 0, 2, 0, 5, 21. How do you know this is a February 5th, 2021, or is a May 2nd, 2021? Because it's order of this information like DD, MMYY, or MMDDYY, there's certainly this different time. Another example is the timestamp. We all use, most of us use Zoom, WebEx, or Microsoft Teams for our group meetings and talk to your colleagues and so on, especially in the last 1 year also. So we use this kind of Zoom and this type of apps a lot. And so this type of app often has a feature to us, allow us to create a timestamp. When we do a meeting recording, we can attach a timestamp. So now the question, so this becomes kind of interesting evidence. Maybe you can say, use this information to show, oh, at that time period, during that time period, a person may not be at the crime scene at all because he was at a Zoom meeting, because this is the recorded Zoom meeting becomes evidence to show he's innocent. But now the question becomes, what timestamp this is about? And so there was a question, so this local device time or is it server time? And so there's a lot of ambiguity there. And there was a case happened in the past, so shows the images taken in one location and if you fly to another location, for example, fly from San Francisco to Chicago. So this time, the timestamp, especially the Zoom meeting timestamp, actually use the local device time. If you save the recording to the local device, they are using the local device time. So that means there's chance, we may confuse ourselves. This is if they're not using server time, then we have no ambiguity. But it's local time, then maybe there's a problem there. You use the same device, you carry the phone from San Francisco to Chicago, and there's 2 different time zones. And then so another challenging issue we are dealing with, there's a lot of kind of interesting apps like Encrypted. They are providing encryption functionalities. They can encrypt messages, encrypt data, like a CoverMe. It becomes kind of very interesting apps. We're seeing kind of a lot of documents, a lot of kind of news coverage about this app, even though it's not that popular comparable to Facebook Messenger and so on. But this being used by the criminals because they claim to provide a military-grade encryption functionalities. For this type of things, if you're seeing a encrypted message, is it recoverable? And certainly, so the question here, so if possible, where we can recover this message, how, where the key to use to encrypt the message, how we can decrypt it, that can be the interesting issue there. And so there are some, the very popular secret texting apps like Telegram, Viber, Silence, a few so on and so forth, that's available on Google Play, and people can download and use them. So there's all these challenges, and also the need from the practitioners motivate us to start work on this EviHunter project. So the EviHunter project trying to analyze the data flow inside the apps from the starting point when the evidence of data is generated and where it's being processed inside the app, eventually go to the sinks. The sinks means either we are writing the evidence into a files in a file system or the cache in the memory space or into a SQLite database, or sometimes we use an external server to process and store those evidence. So we develop a set of toolkits, a set of tools we name as EviHunter. And so EviHunter can help us to understand what and where evidence or artifacts generated by the apps. And then we given an image obtained from a device file system, a particular type of evidence or data, for example, location and time, we can identify which files on the device that contain the type of evidence or data, given the list of apps on the device. And with this EviHunter tools, we are building a Android app forensic artifact database. Tentatively, we have named as AlphaDB. And so similarly, we are working with a DC3, DoD DC3 Cybercrime Center on the digital forensic artifact catalog. So we are building this database to help the practitioner and investigators. And so instead of doing the manual work, we just simply query the database and get the list of evidence the list of apps generate save on the phone devices or on the server, and we can recover. And this can help us to speed up the process, the case process, process. And so, and we build this database. This shows you a very short video to show you how we can use it.
Android app database. This is kind of the welcoming screen. This is only a portion of what we actually have in the database, but you can see kind of what stores we're pulling from with our web crawlers. And if we go up here, we can search for some. Pick one in particular. And you can see kind of some of the information we've gathered online. You can see the developers or actually go to the actual web page. But on the left, you can see some of the information that we've just gathered from the actual app stores. Nothing special here, but just kind of something from the websites through the web crawlers, so you can get kind of like the sizes and some of the permissions that's is actually needed for the app. And on the right, you can actually see the results of going through the EviHunter tool and some of the evidence paths, including the evidence types and where they actually are, including some of the versions and the changes for each version. This is Google Play, so we only have really one version of that. But if you go to some other apps, you can look at multiple versions, and they all have different permissions for them.
Yeah, this short demo video created by my student, Justin Cornan. And so this shows you also how the investigator can utilize this information, this database for the case work. And they can just simply simple query instead of doing a manual search, and which takes time, and it's much faster and much more accurate than the manual process and so on. And then so you might have questions. So with EviHunter, how the EviHunter can help law enforcement investigators? And so with the EviHunter, investigator can now quickly and easily collect and analyze evidence. Go for self significantly use the we are only from 1 to 2 days, as we mentioned at the beginning, to 15 to 20 minutes. And then we try to improve the accuracy and evidence handling from collection to evidence analysis to reporting. And also we provide a few advanced capabilities, for example, help the investigator find a particular type of forensic artifacts and with a precise understanding of its meanings. And also for a given app, we can report a list of all the forensic artifacts that app can generate. And we also can help the investigator to answer questions, whether a particular type of apps and what app has certain class information, for example, and location information. Using other apps information, we can answer, and also we can addressing the questions in forensic investigation. And we have a few high-level use cases to help in-field decisions, and so they can simply type of evidence that they make for the examination. Automation questions.
For those of you still in this room, For the presentation, it looks like Yang just lost his connection completely and was kicked off. We'll have him rejoin us as soon as he's able. It looks like he's back. Yang, it looks like you're back but muted, and you're no longer sharing.
Sorry. Here I apologize because of time limitation, and also we like to apologize at front because the next several slides actually has the technical details about EviHunter. And so I completely understand not all of you have a computer science, computer engineering background, and may have difficulty to understand, understand the technical details of EviHunter, but I try to stay at high level. And so we have two different type of tools. One is a static EviHunter. We take the app APK, which is the file everyone can download from the Google Play and other app stores, with as an input. And then the EviHunter will analyze APK and to try using forward analysis and propagation rules to follow how data generated and how it's being processed in the app, and eventually write into a sync and become evidence. And then we have a small.
This is a video showing the process of static EviHunter analyzing an application and generating the result. Static EviHunter leverages SOT to transform an Android app to Jimple code, a 3-address intermediate representation. IC3 to create interconnected component communication models. FlowDroid to build call graphs and entry points. Then, EviHunter performs forward analysis of the Jimple code to detect the data flow from a source method which may access user's location or store user's browsing history, etc., to a sync method which write this evidentiary data to file or send over to third-party server. We created several web crawlers to automatically collect apps from different application markets and feed to EviHunter. In order to analyze a large number of apps, we set a 3-minute timeout for each real-world app analysis and upload the analysis results to our forensic Android app database.
And then another tool is a dynamic tool. We actually build this tool in modified Android system, and such that we can actually use a real phone device or emulator and to run the app and try to discover or identify the forensic artifacts from the app.
This is a video showing the process of dynamic EviHunter. Upon launching an application, Android system checks if it is necessary to execute native code either because of JNI or compiled code available under normal condition. If not, it will enter interpreter which loops over Dalvik bytecode and executes instructions accordingly. Thus, we modified the Android operating system, where we forced the system always enter interpreter and inserted taint propagation code into the interpreter. We leverage the source and sync method list from SUSE and report the file paths which may contain evidentiary data. We install our modified version operating system to an Android device connected with PC and launch the auto-testing script. We use ADB command to start auto-testing and specify the application list. As you can see on the left-hand side, it shows the screen recording during the analysis. In order to analyze each application thoroughly, we would like to trigger as many features as possible. That's why we leverage Monkey to generate pseudo-random streams of user events such as clicks, touches, or gestures, as well as a number of system-level events. We set a 2 hours testing time limit for each application. The auto-testing script would install an application from the pool, run and test the app, uninstall it, and test the next one. The analysis result is stored in JSON format. It documents the package name and version as well as other metadata we collected from App Market. It also reports the file paths which contain the evidences as well as evidence type. We cross-validate the analysis result between static and dynamic EviHunter and upload the integrated results to our forensic Android app database.
So we hope that the EviHunter technology can help the practitioners, the investigators, and forensic law enforcement organizations to reduce their case backlogs and also improve the speed processing the casework and so on. As a future step of EviHunter, we are trying to continue to work on EviHunter to keep up with the growing numbers and rapidly evolving mobile apps. We have seen the Android operating system being updated from time to time, and right now we are seeing the Android 12 version 12 is being used and being installed, and also the number of apps, new apps being uploaded to Google Play and other app stores. And so we need to deal with those issues. And also there are several other challenging issues like a software obfuscation and people using kind of special tools to convert the app code into a format that is difficult to analyze. And so we are seeing that kind of trend, and people are using the software obfuscators and so on. And also seeing the hardware platform also being evolved and further developed from time to time. So we try to do continue this EviHunter to keep up those things with those kind of things. And the second thing is we try to work with law enforcement practitioners. And so at our state at CSAFE, we are establishing a more like a prototype of AlphaDB, the Android app forensic artifact database. And we hope to deploy an operational AlphaDB for law enforcement practitioners. And so we like to explore further about the feasibility of working with US government like FBI, DOD, or NIST to host the operational AlphaDB and such that so we can have better access control and also to help the investigators more directly and so on. But certainly, so the EviHunter team we will work with you and looking forward to working with other partners, EU and other law enforcement practitioners to utilize the EviHunter to unlock the full potential of the mobile forensics and to fulfill the practitioners' mission and so on. And thank you very much. And my name is Yun Guan, and this is the email address from Iowa State University. Thank you. So if you have any questions or any suggestions, then feel free to contact us or let us know. And also due to the time limitation, so we were not able to go into the technical details, but we have offered to schedule a separate personal meetings with you if you have interest in to utilize EviHunter and also get access to AlphaDB to find a way to help you on the casework, and certainly so we can talk to each other, we can collaborate with each other in the near future. Thank you.